Hi everyone. So in this video we'll discuss one form of regularization that's very common and actually very interesting to study, which is dataset augmentation. And what it means is that you basically are given a set of training examples. Let's say I'm given 1000 examples for a certain task. I create out of them much more than the 1000 examples. So maybe for every example I create 10 examples out of it. And the way I do that is that I think I use my expert or domain knowledge about the problem or the task at hand. And I think of all the transformations that my classifier should be invariant to. So for example, if I'm detecting an object like a pen like this in an image, then I want my classifier to figure out that this is a pen, even if the image looks like this, or like this, or like this, or even rotating in the other direction. So I take one image of the pen and then I create another image by rotating 45 degrees to the left, let's say. And then I take a third image and I rotate 45 degrees to the right. So for every image in the training examples, I do these rotations, I create multiple images, and I train the classifier with the augmented data set. Right? To imagine the impact of this, remember when we discussed ReLU, we said that absolute value ReLU, which is basically taking the absolute value, so it outputs the magnitude of the value, right? So whether it's a negative or positive, it outputs a positive value. Or another way of thinking about it is that the alpha or the ReLU coefficient is -1 for absolute value ReLU. We said that this is useful for recognizing objects in images that could have different polarized illuminations, right? So if I reverse the color encoding or the illumination, the light reflection on the image, then absolute value ReLU is good for detecting objects in such scenarios, under such variations, right? So you could think of another variant of ReLU is to have the ReLU coefficient learnable, right? So you could think of if I have the ReLU coefficient learnable and I augment the data set by changing the lighting, right? In such a way, right? Such that I inverse I have this effect that results in absolute value ReLU. So the network will learn that these hidden units should have a ReLU coefficient of -1, right? So by augmenting the data set with transformations that the network should be invariant to, and train the network with these transformations under the same labels, you are effectively telling the network to learn how to be invariant under these transformations, right? Another example is translating images, and this happens a lot. This turns out to be useful a lot in image recognition problems, is translating images by few pixels in each direction that can greatly improve object recognition in images. Other operations are basically rotating, as we just mentioned, or even scaling the images. And that makes actually the scaling thing, it turns out to be very effective in assumptions, in applications where you assume that this image will be seen, like for example, in self-driving cars, will be seen through a camera, right? So it depends on how close the camera is to the image, how the image will be scaled. And you want the same learning algorithm to apply no matter what the exact distance of the camera to the object is, right? So one thing to note here is that we should never use transformations that affect the classification. And that's why we need domain knowledge for dataset augmentation. For example, if I'm recognizing letters, handwritten letters in images, then I should not augment the dataset by introducing horizontal flips, right? Because the B and D will be confused together. If I'm recognizing if it's handwritten recognition of digits, like the MNIST dataset, I should not have 180-degree rotations or vertically flipping the image, because the 6 and 9 will be confused together, right? So in general, you should distinguish based on domain knowledge between the transformations that should affect the classification, and the transformations that should not affect the classification. Now, it's also, so it's not just useful for images, it's useful in many applications, as you can imagine. And a very natural application to dataset augmentation is speech recognition, right? So imagine I'm training the Amazon Alexa, right? So I want it to be robust to different voice tones and different accents. Right, so I want the machine learning model to learn regardless of the, how to interpret what's being said regardless of the voice tone or the accent. So maybe I take one data set collected from one human being, and then I do these transformations to change the voice tone or change the accent and augment the data set. Out of one person, I create an artificial augmented data set of 10 persons, let's say. Now, it doesn't have to follow the semantics exactly, because maybe I inject noise at the input as a form of dataset augmentation. Now, that could be very useful in wireless signals, for example, right? Because wireless signals come over the air, right? And there is noise in that channel. That noise can have different magnitude or different power, right? So maybe I collect data at a certain signal to noise ratio, and then using a model for the noise, let's say additive wide Gaussian noise, I augment this data set with other SNR values or other signal to noise ratios, right? And one other example for augmenting the data set with noise is the adversarial machine learning problem, which we'll have a project in that course on it. And that problem is basically assuming that there is an adversary that's intentionally introducing perturbations to the input data such that the classifier outputs a wrong outcome. Then one method of combating adversarial perturbations is something called adversarial training, which is basically simulating what the adversary would do, and then augmenting the input data with the simulated adversarially perturbed data, right? Now, something to note here is that it doesn't have to be that the changes I make happen at the input level. Maybe I make them at the features, the hidden features level, right? So maybe I want the network to be invariant to certain changes in the abstract concepts. For example, if it's edges, if I want to perturb this data, let's say the first layer is learning to detect edges, I want it to be robust even if I perturb the output of these hidden layers by a little bit, right? And actually dropout is one way of doing this, but by noise multiplication, not noise addition, right? So you could think of it in biology. So this is one of the very interesting and effective techniques in machine learning, and it is inspired by biology, right? You could think of when you're dreaming, you're imagining scenarios sometimes that never happened before as a form of data set augmentation, so that you learn how to react to these scenarios. You could think of when you watch a movie and you watch someone passing the road carelessly and gets hit by a car, and then you try to simulate how did it feel. That's an experience you never had, but you're learning that what you should do in these scenarios, or you're learning that you should not pass the road carelessly because you augmented the set of experiences that you get through with these set of experiences that you imagined or dreamed about, so that you improve your learning capacity. Now, one last thing to note about this interesting technique is that you could use maybe a separate machine learning model to learn how the transformations that the original model should be invariant to. And one possible way to do this is what's known as Gans, or generative adversarial networks, which is using tension between two different models. One is generating examples and one is classifying the examples. And also we will have a project on Gans. Sounds good? Thank you.